All right, welcome back. And today we are going to go back to school. And what do I mean by that? I mean that we are going to look at a question called course schedule. Now, it's pretty interesting. This question, course schedule, is, I'd say it's a pretty fundamental question, not because of the question itself, but because of what we're going to be using. All right, cool. So let's look at it first. First, this question sounds kind of interesting, and you might not know how to do it right away, but then once you understand the right data structure to use, it becomes very easy. Okay, so let's read the question. There are a total of n courses you have to take, labeled 0 to n-1. That's just to make it easier. You could think of it as like CS 101, CS 102, blah, blah, blah. Some courses may have prerequisites. For example, to take course 0, you have to take course 1, which is expressed as pair 0, 1. Given a total number of courses and a list of prerequisite pairs, is it possible to finish all courses? Now basically the question is all about if it's even possible. Like, imagine if there's a list of courses at school and there's some courses that have a prerequisite that you can't even get, then obviously that's impossible, right? So yeah, so basically we want to check if there's any inconsistencies in the course schedule. Now let's talk about this a little bit more, or let's try to think of it. Now, like, let's look at the first example, and then we'll do an example on the iPad. So here's 2 saying that there's courses from 0 to 1, and then there are 2 courses to take, blah, blah, blah. Yeah, and then the first one, so we know there's 2 courses, so there's course number 0 and course number 1, right? Should I write it bigger? 0 and 1. Okay, cool. And then we know that there are 2 courses. To take course 1, you should have finished course 0. All right, so then course 0 will unlock your ability to take 1. We'll just put that as an arrow, right? So what you can do is you can take this course complete. So then you're allowed to take this course complete. Imagine if the input was like 2 and empty, then it would have been 0 and 1, and you could have taken either one at like first. So it doesn't really matter. So imagine if there's no prerequisites, then obviously it's true. Now the second example, you have the same thing, 2 course. So the input is 2, and then you got 0, 1 and 1, 0. All right, so that means you have 0 and 1 as the course, but then you have an arrow here and then also an arrow here. So obviously this should return true, this should return false. And the reason why is because I want to take course 0, but I can't, because I know that I need to take course 1 before I take course 0. All right, fine, let's take course 1. Oh wait, in course 1 you have to take course 0 before course 1. That's impossible. And there you go, that's impossible. So this is like a toy example. I'll just do another example just to make it more clear. Imagine input is 3 and you have 0, 1, 1, 2, and then 2, 0. Right, so basically you have this. All right, you have like this, and then like this. Same thing, right? This should return false, because to take course 0, you have to take course 2. Okay, but to take course 2, you have to take course 1. But then to take course 1, you have to take course 0, so that's just impossible. If we remove this edge, if we remove this one, then that would be possible, because you could take 0, and then you take 1, and then you take 2, and that would be possible. So does it look kind of familiar to you? Yes, it does look familiar, because we have nodes and also edges. So what does that mean? It means this is actually a graph problem. And once you realize that it's a graph problem, it becomes so much easier. Now the next step to make it even easier is to understand what algorithm we should use. Now we realize when can we, like if you just like here, when can we take the courses and when can we not? So like we said again, whenever there's an impossibility, like there's no reason I could finish this course because I need that course, but for that course I need this course, which blah blah blah, right? So that means that there's like a cycle, right? So in terms of graph, because whenever it's impossible, it means there's a cycle in the graph, and this is a directed graph because there's arrows. So what do? All you can do is you could make all of these edges. These are all the edges that they give you. Make that into a graph and then traverse the graph to see if there's any cycles in the graph. And then if there is a cycle, it means it's impossible and you return false. So this question is actually a question detecting cycles in a directed graph, but masked into a coarse question. So that's pretty much it. So if you know how to detect cycles in a directed graph, you already know how to solve this question. But we'll just solve it again, and then so that we could like refresh our memories. Okay. So how do you detect cycles in a graph? Well, it's pretty simple. All you have to do, like intuitively, imagine you have a bunch of nodes, right? Bunch of nodes. And then you could go here, go here, go here, and then maybe they're not even connected, these graphs. Then you know that's fine. And then what happens when, like what would be your kind of a brute force way to see if there's a cycle in the graph? Well, what you can do is you go to one node, right? And then you traverse to all the node it can go to. And then once it's red, it's already visited, right? And then if ever you encounter something again, then it means that there is a cycle, right? So let me try to explain. So imagine if, you take each node and then you traverse, and then you see if there's any, if you go back to a node that you've seen before. So imagine we choose this node. So we see this as visited, and then that's pretty much it because the arrows are done. And then imagine if we're visiting this one, what happens is you're gonna visit this guy, and then you're gonna move on to this, and then you're gonna move on to here, right? Now let's make it a little bit more complicated. Imagine we have like that, okay? And then what you'll do is you'll visit here, and then you'll visit both of these at the same time, and then you'll visit these guys. And then when you're done, you're done. So then there is no cycles here, or at least there's no cycles in this subgraph. What you have to do is you have to do it on every single node, because you have to make sure every single node is okay, right? Because I could give you an example. Imagine if there's another arrow like here, like this one, right? So if we use this guy, yes, it seems like there's no cycles here, but we haven't looked at these guys yet. And then once we do look at these guys, and in the second run, we check this guy, and then we'll look at this guy, but then we're not done. And then we look back at this node and realize it's already visited. That's when you know there is a cycle. So whenever you start at a node and you start visiting a bunch of nodes, and then you visit a node that has already been visited during your subset, then that means there is a cycle, right? So that's how you do it. And how do you do that? Well, you need a bunch of data structure. The first data structure is you need a way to represent your graph. Usually in a way to represent your graph, it's I like to have a hash map of what do they call it? They usually call it a associated array. No, wait, adjacent nodes. I forgot what they call it, but basically it's a hash map. And then the keys are each node. Let's say that's 1, 2, 3, 4, 5, 6, 7, right? Let's say this is it. And then 1 would be here, and then it will be an empty array because it points to no one. 2 points to 1, so it has an array of 1. And then 3 would be 7 because it points to 7. 4 points to 2 and 6, 2 and 6. And then 5 points to nothing, so empty. And then 6 points to 5. And 7 points to 6 and 3, right? Let me just Google what it's called, ways to represent a graph. Adjacent list, yeah, that's it. Okay, so we're using adjacency lists to represent our graph. There's two more ways of doing it. There's adjacency matrix and there's edge lists. Each of them are good on their own ways, but in this one, this is the best because what we want to do is we want to, given a node, we want to know all the other nodes that are adjacent to it. That gives us like advantage here. All right, cool. So now how do you detect a cycle? Well, if you look at here on the algorithm, we go on each node. So we could say like, for each node, and then we have like a visited set. Like imagine this is your set of visited, right? And then for this one, if we go to 1, the visit, we already visited 1, so we keep a number here, and then we keep a number, and then once we're done visiting this node, we reset, and then we have a new visited. And then once we do it many times, you'll realize, like, let's do 4, for example. If we start at 4, we would have visited 4, and then we iterate over 2 and 6, and then 2 and 6. And how do you visit them? You could do breadth first search or depth first search. I'm not going to go through it now because you should be able to know. You should know how to do that already. And then 2, 6, and then 2 will visit 1, and then 5. So then you're visited, there's always a bunch of numbers. Now imagine if we visit 3. What would that look like would be I visited 3, and then I visited 7, and then at 7, I visit 6 and 3 again. But then once I see that 3 is already in here, then I return false because there's a cycle, right? So basically what you need is you need a graph representation where here it's a hash map of lists. And then you also need a visited set. So this is kind of like a hash set. And actually that's it, that's all you need. And then you just have to iterate over each node. And then for each node, you call, like a depth first search or breadth first search, and then you update the visited, the visited set. All right, easy peasy. All right, let's do it in code. So like I said before, first you need the graph, and the graph is what was it again? Adjacency. I keep forgetting. Adjacency list. And then so then what you need is a dictionary where you give the key, and then for each key it gives you a list. So default dictionary list, and what that means is that if I don't initialize it as anything, it's an empty list. Yeah, it's like a Python thing. So then we're gonna go for each of the edge. It's called prerequisites. That's the data structure that they give us. And then what we want to do is we want to look at the edge, the first one, because the first number is like where the arrow starts in terms of prerequisite, right? It's like it goes that way. So edge 0, and then append whatever the second number is, which is like the prerequisite to take whatever course it needs. And then we'll also define a path, which is just a set. Like I said before, path just means like visited. I'll call it path because in each node that we visit, we're gonna create a path. But if we run into the path again, then it means it's bad. Maybe I should call it visited. Maybe it's more. Maybe it's easier to understand. Let's call it visited. Right, and then we're gonna have another function, and this function is the one we call where we go into it, like we go into the vertex, and then we go across. So we go into it, and then we do a breadth first search. Yeah, we just do breadth first search. Okay. Now I'm gonna do depth first search. There's no particular reason. The reason I chose this is because I like recursion. Recursion is really easy to implement. So yeah, that's pretty much it. So what happens in depth first search? You first add, you have to make sure you have a path. Oh, sorry, not the path. I want the visited. The visited, you add the vertex that you're in now, and then for each of the neighbor, you call it recursively. Right? So if neighbor in visited. So like I said before, if you visited it, then that's done. Because if you're visiting a visited node currently, then it means you have a cycle, and then you have to like end it already. And then here's where we call recursively. Neighbor. We call recursively visit neighbor, return true. And then here, let me just explain to you. True if there is a cycle, false if not. Got it. Okay. And then once we're done, path, remove vertex. Yep. So, yeah. And the reason why we have to remove it, it's kind of like backtracking, but it's more like, so my set remains empty after I'm done, because I don't want it. Because imagine if I'm visiting one vertex, but then I visit the next vertex, I want my why did I say path? I want my visited to be reset. Okay, cool. And then if it's all fine and I don't encounter a visited node, then I return false, which means there's no cycle. So remember what we did? So now we have that subfunction. What we want to do is call it on every node. So for I in range num courses, which is every node, we're gonna visit node number I, and then if it returns true, it means there's a cycle. Then we return false, because the question tells us to return false if there is a cycle. And then after all of that, if all of them is fine, then we return true at the end. So yeah, let's try to run this. Default dict is not defined. Oopsies. Neighbor, how do you spell neighbor? It doesn't matter. Okay, I'll just do that. Okay, cool. So this test worked, and then let's submit it again. All right, and it works perfectly fine. So yeah, so that's pretty much how you do it. There's like there's other ways you can do it too. I mean, if you go to discuss, you can do like union find, depth first search. You can also do it breadth first search style. Yeah, there's like a lot of different ones that you can do. Most of the people use breadth first search, depth first search. You could kind of look into it too. Front to end to front, front to end. Yeah, interesting. So okay, yeah, that's pretty much it. And then in terms of time complexity, it's just you have to visit like the whole graph, probably like a few times. So then it's kind of like a imagine if n was a number, then it would be n squared. The reason why is because imagine if for each node you have to visit all of the nodes, and then they're all kind of connected, then you have to do that. And then in terms of like the size, the space complexity, you do need the graph. So that data structure, you need every single node, which is O of n. And then it's possible that for each node you have O of n numbers, so it could be n squared. So space is n squared, and then also time is n squared. All right, cool. So I hope this was interesting, and this is how you detect a cycle. And remember, always think of the question, patience, and then try to map it into an algorithm you already know, or a data structure. All right, thank you so much, and see you next time.